Okay, all right, folks. So let's start with lecture 8, which is on system calls exit, wait, and exec. Okay, uh, we have already studied one system call which is fork. Let's look at some of these. These are very interesting, right? And it takes a while to grasp the concepts, but once you do programming, you will get feel for it. Okay. Uh, of course, I have taken contents from many places, primarily from this book. That's Three Easy Pieces. A very nicely written book, and I will urge you to please go through the chapter, and of course some other resources. So I try, when I make PPT, I try to make as much visual, in the sense I try to get diagrams of figures, right? So and wherever I get those diagrams which can depict the concept, I try to put into PPT. So that helps anybody who's reading it. Actually, it helps me a lot to visualize it. And visualization, as we discussed, is very important. Okay. All right. Okay, so we'll study these three system calls. And most of the discussion is centered around Linux or Unix, right? So most of the discussion in this course, we are following Linux or Unix. Around Linux, it may not be exactly the same, but because OS is also changing, like something we call PCB in previous classes, process control block, is called process descriptor in new Linux, right? So concepts remain same, data structures might change slightly. Okay, so far we have studied the following. Last course that we studied last semester, we have understood how processor work, and on top of that we have OS. So processor itself gives you some kind of virtualized world, but it's a hardware. Somebody has to manage that hardware, right? So and then if there are multiple users or processes on top, then all of them should feel that the whole computer is for themselves. And we have seen one very important virtualization concept, which is the virtual memory, okay, in our architecture course. And then OS role is to give this, there are multiple roles that we have studied, but primarily to help user processes to run properly, or and also efficiently utilize resources, and also provide security. Okay, so these are some of the roles that we have studied in the past. But remember that interaction between something that is on top, user processes or library, happens only through system call. Okay, remember this thing, right? And then we have seen that most of the programs that we write using OS library or library provided to us, like libc or many other libraries, right? Simple reason is that for doing even file copying from one file to another may require 30 or 40 system calls. So why complicate the programming and make a lot of errors in that, and when you have complete functionality available on top through library. And also other thing is that whatever be the OS below, or whatever changes in OS below, maybe some system calls are added, as processor changes, right? So all these things are need not, it should not be visible to users on top, right? So OS is going to hide some of these, and then in turn OS libraries are going to hide others. For example, if you're using Linux versus Windows, or Linux or Windows, okay, or Mac OS or whatever, if the library implementation is taking care of that, then interface on top remains the same. Okay, so whether you're now OS library implementation might change, but the API is given by libraries will remain the same. So you write C program for Windows, where OS is Windows, or Linux, OS library hides that detail. You need not know what is OS running inside. Okay, all right. Okay, any question you had on previous lecture? on fork? No? All right. So what we have studied in the last class, fork creates a new child process. Okay, and of course all processes are created by forking from parent. Okay, and init is the first process. So when we fork, we create exact replica of the process. Code and data elements remain the same. Okay, only process name changes, right? There are minor changes, but process does exactly the same thing. Okay, and it start execution from almost same points where fork has happened, right? So the next instruction from that, both processes after forking run. Okay, so today we'll see that how process can be terminated, and and then two important calls, system calls exec and wait. All right. Okay, so we will go into the concepts, primary concepts. Okay, and I will urge you to go into details, because if we get into detailed syntax of these system calls, it will take a lot of time. And secondly, there are many variations within system calls. For example, exec alone has many variants, right? So remember that we are not studying here the details of programming, because these are also part of programming. C programming book, you'll find many of these, or Linux books you'll find, but we are looking mainly at the concepts. Once you understand concepts, then details, syntax of the various system calls and library calls becomes very easy to understand. Okay, so creating a process, we know that initially there is just one process, and from that we can fork another process. For example, from any process that's running, other process can be forked. Okay, so once we fork the process, we have seen we are creating exactly similar process with minor changes. Okay, I will not use the same, exactly same, but similar process. So code data remains the same, file descriptors, etc. remains the same. PCB is different. Okay, and however, they are running in their own address space. So this guy has address space P1. So for example, this process has address space that we have studied, which we call memory image. This guy will also have its memory image. Okay, code, suppose this is a code part, the code remains the same. When fork has happened, all the values of stack, etc., where variables are same, remains the same. Okay, process descriptor might have some changes. When you say process descriptor, actually process control block. For example, process ID, PP ID, process parents ID, and for some values are different. So that we have studied in the last class, like ID changes, right, and so on. Okay, is it fine? Any question? Okay, all right. Okay, now let's look at how process can exit, right? Or a process is running and then process job is over, and so it has to exit. Okay, so we call it termination. Okay, process termination. This is much better word than killing, a word called killed or died. Okay, so a process may decide to die or end. Okay, so it may voluntarily call, or in the code there will be instruction called exit. Okay, so exit will happen. So process will once process executes this system called exit, then process terminates. Okay, is by so it comes to end. Second is that a parent may decide to terminate a process. Okay, so process may be running, but the parent decides that something needs to be done about the process, so it can use a process system call called kill. Okay. Third is that process receives a signal. Now, note that we will study signal in detail, but for example, when you do control D, or or some of those, or escape or something, so that sends a signal. Okay, and so if there is a terminate signal, then that process gets terminated. Okay, all right. Okay, now these are the three important ways. The next question is that on death, what will happen? See, death in general, for whether human being or something, is recycling, right? A little philosophical, but think that what is a death is a recycling of our body elements. Okay, it gets recycled. If imagine nobody would have died, then nobody would have, world would have been full with all people who have been there so long, and resources would have been falling short, because it's just absolutely recycling that's happening. Same is in computer. If the processes are not terminated, is by voluntary, it means that, I mean, the process comes to the end. I mean, when it's running, it comes to end, like our lives comes to end. Okay, there is natural death, or it could be killed by some terrorist, right? Somebody can get killed, so that's involuntary. Person may not want to die, but somebody is telling that your time is over now, go. Okay, or it could be terminate signal, right, which is again involuntary. Somebody somebody gets died because of some signal, maybe gets a virus or something, or poisoning or something, right? So so just think in this term that recycling is necessary. If processes are not recycled, then system will filled of processes which are not needed, and it's meaningless, right? The system will not work. Same is true of life, that recycling of us is required sometime or other. Okay, so what happens in death? All the resources that we have are reclaimed. Okay, so in the case of process, all memory or all process exists in memory, we know that. Okay, that is taken off. Okay, so some other process can use, so basically memory is freed up. Okay, and make process unrunnable. Now, of course, when it's freed up, then it cannot be made runnable. Okay, and what is next thing now? But process, now once process is kills itself for by exit call, it comes to zombie state, that we'll study later, right? It means that it has its own descriptor. I mean, PCB remains alive, because the parent of the process may want to use some information about the child. Okay, so so the process in zombie state. Okay, it means that process descriptor or PCB remains alive. Okay, and at the then we'll see that system sometime or other has to clean that stuff, right? So we'll look at that. Once syscall, that will wait syscall. Once we execute wait syscall, then this PCB also can be reclaimed. Okay, so we'll come to that little later. So now let's move into the second system call, which is wait. So it means the parent process is waiting for his children, one of the child or a specific child, to terminate. Okay, to get killed, or to because of voluntary or because of something else. Okay, so parent can wait for child to die by executing wait signal call. Okay, this is quite useful for parent to wait for child process to finish whatever what it has been doing. So there maybe you can think of scenarios where child is doing something, but parent is let child complete and then parent process will continue from there. Okay. So let's look at the scenario here. Okay, but before that, on success, okay, when wait execution of syscall is successful, okay, it successful means that child dies. Okay, then this call will return, because we are using this call in as part of program, so it will return some value. Okay, what it returns is process ID of terminated child. Okay, if the child dies because waiting for child to die, then it will as a part of return, the parent process will get ID, process ID of the terminated child. Otherwise, if there is error, okay, then it will get -1. For example, child doesn't exist and it waits, right? So this system call will give -1. Okay, so now let's look at the scenario. There is one process initially, okay, and there is a fork, the process fork. So exact 2 copies are made, similar 2 copies are made. Okay, so now this copy here and the copy here, say this is P and this is C process, are similar, that we have studied. Okay, then we run. Now note that if both are doing same thing, then it's not very useful in most of scenarios. Then we can create a separate process from the child process by running some different code. This is exec call, which we are going to study next. Okay, and then this new process, say C changes into say C1 or maybe D. Okay, and then it runs, it has done its job and want to exit. So it will run this system called exit. And now this process here, parent process, has run a wait call, system call. It is now waiting for this child to complete. When this child completes, then it resumes our activity. Okay. Any question? Very good. Wait. Okay, then and there are multiple folks have happened in the past. It means there are children. Instead of one child, there are children. Okay, and then when we execute this wait, then process waits for a child to terminate. So one of the many, the one which gets terminated first, that's fine. Then wait unblocks itself and moves away or proceeds, right? Okay, and if the caller has no children, then of course the error condition. All right, and if process waits for a specific child, then it has to mention in it what child ID. So it waits for a specific child to get terminated. Okay, and then it can move further. Okay, all right, but just that will explain the concepts. All right, so let's look at this code. Okay, this again I have taken from 3 Pieces book, so you can read that if you don't understand it here, but you can get plenty of the programs, or you can write by yourself. Okay, so it's very simple program, and that we have last class we have studied part of that. Okay, so we are okay. This is the beginning of the program, main function or main program, and then here what we are doing. So it's printing hello world and its own process ID. So initially there is one process, it will print its own ID. Okay, and then what are we doing? We are forking. Okay, forking is returning the child process ID. So right now from at this instant there are two processes that has been created. Now both processes are running. Okay, so we come here. If it's a child process, I'm sorry, if the return value is 0, which is for child, then this is running. Okay, so this will have, this is parent process, child process, both are running these instructions. And for this RC is equal to 0, and for this RC is equal to child ID. Okay, all right. So if if RC is equal to 0, it means this child process is running. Otherwise, code will not come here. Only here in this instance, does the code, this part of the code will be executed. Okay. Then it will print hello, I am the child, and its own PID will be printed with get PID system call. Okay, so child runs get PID and then prints its own PID with and with this string or text, right? Okay, and then sleeps for 1 second, because we can avoid sleep also. It's not that sleeps means that it waits, does nothing for 1 second. Okay, else it means that it is the parent process. Then what it does? It says WC is equal to wait null. Now here, notice a WC, not RC, right? So the new integer we are defining, and says that it is a return value of wait null. Okay, so it's a waiting for any of his child to die. Okay, all right. Okay, so what will it now? It will say printf hello, I am the parent of this. Then it will print WC. Okay, WC is what? The child. See, when process is waiting and when it's successful, it returns child's ID, terminated child's ID. So WC will print child's ID. Okay, and okay, and here at this point it will print its own ID. Okay, and then we are printing PID is basically parent process ID. So basically, if you relook at it, it will print the following things. Hello, I am parent of this some process which corresponds to RC here. Okay, RC is child ID. We know. No, just a minute. Okay. Okay, RC is child ID. Because right now we are running a parent process, so RC value that returns from this call here is child ID. WC is what? WC is also child ID. That has got it to wait, and then get PID is own PID, process ID, right? So basically, it will print child's ID, then again child's ID, and its own ID. Okay. So now when we run this, we'll get something like this. Okay, so basically first process hello world it will print here from here. Okay, from here, and then it will print hello. Now child will terminate because process is waiting, right? So even if process is scheduled, it's waiting at this point in time. Here is this statement. After that, then no execution. Means this statement will not be executed. Printf will not be executed. Now, okay, how many times is scheduled? Schedule in the sense that OS brings into the processor and runs, but it will hold on here, and the child will, whenever child gets time, it will continue to run and finally terminate. Okay, so shall we look at this execution of this? Very simple. Actually, it doesn't require any. What is a just a minute? What is the P2? Wow. Just a minute. Okay, let me just switch back. Give me a minute. Okay. No, so then sorry, I'm just a minute. Let me go to desktop then. Okay. Okay, just a minute. Here we are. Okay, and I have to go to p2.c. There is p2.c. This is here is p2.c. Okay, so I have compiled it already. Let me see, where am I? Okay, I'm at right place. Again, let's compile gcc p2.c op2. It will overwrite whatever is there. Okay. Okay, so now we run it. So basically, P2. So it says that, yeah. So you could see there was little delay because of 1 second delay. So it after this statement is printing, there's 1 second delay. If you change it to 5 seconds, you can see there's a more wait. Okay, so I am child. So this process terminated first, and then control comes to the parent process. The parent process now terminates, and it prints whatever is I am parent of the child ID. You note that this 14530 and 14530 both correspond to the same child process, and this is a parent ID. All right. Okay. Let me switch back. Give me a minute. Okay, let me switch back to code. Okay, iPad. So, okay. All right, any question in this one?
Sir, could you tell why have you written weight of null?
Weight of null, because we are not, first thing is that we are not trying to get any other information about child process, right? So child process, some information if you want to read, then we can. So weight in general, it weight in general waits for a child to die, and we are not getting any information, any status information, right? If you see, so when you put null, it means that you are not expecting any information from child process that has died. Okay, so this is one of the arguments that we have. We have seen that we have some arguments here. Okay, so we are not doing that right now. I'm sorry. There's somewhere other. Okay. Right. So termination status of the child can be obtained from the argument that we are not doing right now. So there is a you can get some information from the child process. Okay. All right. So this
Yes,
is simple. Now, if you use instead of this a system called PID. I'm sorry. What is that? Sorry. Wait for a wait ID, wait PID. Then you have to specify inside as an argument what exactly which process you want to wait for is death, right? A specific child, wait for a specific child's death. Okay, so wait is very simple. It takes waits for one of the child to die. All right, shall we move ahead? Any question?
Yes, sir. Sir, why both of the loops have run, sir, in the code?
See, once we create two processes. Okay. All right. Now let's look at system call exec. All right. See, we have seen that, when we fork, a process forks, right? Say parent process forks, it creates a child process created, and both are running the same code. Actually from the same instruction, similar next instruction, the both run, right? And is it a good thing? Sorry, just a minute. Okay, is it a good thing? No. See, sometimes you may use it, but mostly, both are running the same code is not too useful. So what we need to do is that in the child process needs to do something else. Okay, so we can launch into child process a new executable program. Okay. So now in order to do that, we use this system call called exec. Okay, so the child can now, with this, of course, it will have some arguments, and this argument will tell what to run. So let's assume we want to run a program called p1 dot say exe. Okay, then of course this program will also require some arguments, right? So we also need to specify some arguments for this program. Two things, right? So when you say that I am running a program, then of course it will need some arguments, right, that we need to pass. So we have at least two fields we need. One is that what you want to run, okay, and second is that what parameters that new process that or new code that's in execution needs. So that needs to be specified by is specified in exec. And who is running exec? Who is running exec? Is any process can run exec. Okay, so it's like any process is changing itself at runtime. Yeah, very interesting concept, right? Okay, so it means that I mean, if you have synonym or similar, if you visualize, it's like a human being transforms itself into a cow during the lifetime, right? So it's something like this. So it's another visualization could be running a car and changing at the same time its main character, which is engine at runtime, right? So it's a very interesting concept if you visualize it, right? I mean, the process is running and suddenly it decides that it needs to change its code and new process, and then from that new process it transforms into new process. All right. Okay. Now after transformation, do we need some return value? If successful, then of course we don't need return value. Okay, and something that we are going to execute, the new code could be a shell script, which is shell script is nothing but a program or an executable file. So obviously exec will require you to specify program you want to run. Okay, so we now look at this way. Of course I have brought in this picture just to give this concept. A process has to transform itself. Okay, it's running some code. Okay, and then there is some file descriptors, etc. Now PCB contains file descriptor, etc., which is in kernel space. So now running exec, it changes itself into this process 2, which will have different code and different data. You can see, I mean, even pictographically, this is white in color, this is blue in color. Actually, it means the code and all stacks are restarted, right? When a new process formed, is exactly like a new process being formed. Okay, all the stacks are cleaned up, etc., etc., because starting from beginning. Okay, note that this new process is starting from beginning. Okay, and however the kernel space, open files, etc., remain the same. And of course, during its own execution of code, it may change all this. kernel, all this PCB will get changed, values will get changed. All right. Okay. Now let's go ahead and try to proceed. Okay, so there are various. So exec is a family of system calls, right? So if you have something like exec, if you write in code, it doesn't work. So it will be one of these. Okay, and wherein what goes inside will change slightly. Where are you taking the values, right? Whether you are defining absolute path or through slash mechanism, or your values are taken from environment, and how you are passing the argument values, other argument values for the process. Okay, so accordingly you have various options available, L, V, E and P. Okay, all right. So let's look at only one of these, which is EXE-CVP. Okay, then basically we have this defines what program we want to run, because you note that original process when execute this one transforms itself. So new code will be defined by this. Okay, which is nothing but you can directly specify file name, or it could be through path. In the directory you have path. Okay, through slash mechanism, so you can define through that. And then this is an argument. It's a array of strings. Okay, which gives a argument value. For example, you say that I am running bash. Okay, so basically you are running a bash program. Okay, and then you want to run ls minus l. Okay, now ls is a program which will go here, and the other arguments, L and many other arguments, if you have, then it will come here. It's just one argument, it's just one value. If there are multiple arguments, it will go into this string array. All right. So when you're defining this array, make sure that you do it properly, because first argument argv0 is always file name. Is should be same as this one. Okay, that goes here, and the last member is null, because it's a null terminated string, null terminated array. So last string of that will be null pointer. Okay, so let's visualize it, and it's a note that it's a very high level diagram of something that we discussed shell just now, right? So this is a shell program that we are running. Note that it's a very high level. We are not going to bits and bytes at this point in time. So there's a shell program is running here. Now you want to run ls. In shell you say ls minus l or something like that. So what we'll do, shell will create 4K process. So now there will be two processes, right? Parent and child. Okay, now both are running the same shell. Now one of these, the child process, needs to convert into ls, corresponding to ls program, right? So now new child is created. So basically in this space we can see that there is now this code is loaded. Okay, and there is a new data and new stack is created and so on. And this, of course, recycled, or is over that. So who does all this? Is done by OS, right? OS creates, when you run this exec command, OS takes responsibility of creating a process with whatever parameters you have defined, all the details given by the system call. All right, any question? Okay, so let's run very small program. Okay, I will not go into it. We can run it, but it will take time. So basically in this one, what are we doing? The same thing that we discussed earlier here. Okay, so we are defining what? we are defining argument values as follows, right? Three arguments, we have to pass on some arguments that we studied now, right? Like with these arguments. So we are now defining the arguments as follows. First is the first argument of that is program name that we want to run. Second is -l. Okay. So now through this string array, this is string array that will have three elements rather. So one is ls, second is l, and third is null string. Okay, third point to null. So basically we define these three here, and then we say exec cvp cmd0, which is ls. So basically we are running, we are telling is ls exec cvp ls, and then this is -l as an argument will come. Okay, so basically second is actually the whole, when we define it, is we define the whole string array. Okay, and the second value, when it's executed, the argument values are taken. Okay, so once new process is created, okay, it will continue to execute there. So it won't, next instruction will not be executed then. All right. So now we have created new one. So that if successful, then of course we have seen that there's no return value, and now this comes into play. All right. So as a result of that, you can see that ls -at will print all this. If you want me to run it, then let me just do it quickly. Oh, it will take time. Okay. Okay, what is this called? p5.c. Let me go to terminal, desktop, screen. Okay, do I have p5.c? Did I create that? Just a minute, let me move. Okay, it's there. Okay, same code. Same, I will skip compilation. Is there? Let me see, it's there. P5 has been compiled, yeah. So if you run it, then we'll print something, right? Yeah. So it will take, these are the my different directories. So I'm running ls. If I run ls here also, ls -l, it will should give me the same result. So it's exactly similar, right? All these files are there in my directory called PC, CP or PC, whatever it is. Okay. Okay, CP, C programs, right? Okay, all right. Any question? Okay. So we know that we have any process can fork itself. So let's assume process P1, it forks into two process. It forks. So basically P1 remains active and then child is created. Okay, we call it C1. Now both are running exactly same code, which is of no use. Okay, then we can run exec system call. Okay, and here we define what the process wants to transform to some program name. Let's assume ls, and then it has to define some parameters -l, for example, or we can define word count and so on. Word count, and then argument of word count will be some new file name, some file name in which we want to count the number. So it could be any or any other program, right? And now this changes into some new process, and then when this now parent of course may want to wait for child to exit because it wants to synchronize certain activity, or the sequence it has planned. So then in order to do that, it executes wait. So it waits for child process to end, And when the child process ends by its own natural death, or when it completes a code execution or through exit call or something, then this parent process proceeds. So these three concepts we have studied in brief, okay, that we have discussed through this one. And note that when the process, so this is a running process, okay, and when it finds out that there is a in the code in execution, this system call comes, then this guy transforms it. This does not exist. Then after execution of this system call, the new process is created, new avatar is created, right? And then all this goes off. So this is a new process after execution of exec call. And what this new process would look like, it depends on what program exe file you are defining, and what data values you are giving. All right, so we have just today looked at these basic concepts. All right, this is another thing. This is how shell program runs, right? So if there is a shell program, when you run ls, it means that now a new program is to be process to be created. So first it forks, creates own copy of it, and then loads into that code corresponding to ls. And various arguments that you pass in -l, etc., is also passed on to this one. All right. All right. Okay. All right. So we'll close now. And if you have any question, please feel free to ask me if you have any.